Let's continue to solve by elimination, but the example that I put up here is not ready to go. The first couple of problems that we've done, we immediately were able to add the left sides together and add the right sides together and get rid of a variable. In this particular example, these x's are not the same but opposite in sign. That's what has been the case. Nor are the coefficients for the y terms. Matter of fact, the coefficients here are 1 and the coefficient here is 1. So what I need to do to solve by elimination is to choose to focus on the variable x's or the variable y's and choose to multiply one of the equations or both of the equations by a value to force the coefficients to be equal but opposite in sign from one another. So you see this plus sign and that minus sign in front of the y terms? It would be easiest if I would just multiply this whole equation by the number 3. I'm going to multiply the whole equation. Multiply by the number 3. Because that would cause this to be a 3y. And this 3y and minus 3y would disappear. So that's why I'm choosing to. I have to multiply both sides of the equation by the 3 to keep the balance in the equation. So 3 times this x will cause that to be a 3x. 3 times that y will cause that to be a 3y. And 4 times 3 will cause that to be a 12. And now I'm ready to eliminate. So this 5x and this 3x is 8x, and those disappear. And on the right here I have a 24, and when I divide both sides by 8, I find out that x is equal to 3. I take that solution and I put it into either of these equations. It's much easier to put into the first equation, so I'm going to put it into x plus y equals 4. So when x is 3, I just need to know what y is, and of course you can see y is equal to 1, but algebraically this is how we show that to ourselves. So the solution to this set is x is 3 and y is 1. I've checked this prior to videotaping. You should do it as well, but I'm just not going to take the time as well. I know it works in the first one, but you should put the 3 in here for x, the 1 in here for y, and see if that's a true statement as well. Let's do another. And I'm going to use some w's and some z's this time. Now this problem is going to require that I multiply both equations by a value to force these coefficients to be equal but opposite in sign. I could either try to make the w's have a 6 and a negative 6 in front of them, because that would be the common multiple of those two, or I could force the z's to be a 12 and a negative 12. Because these signs are already opposite one another, it doesn't require me to multiply by a negative number at all. So I'm going to choose to multiply this whole equation by 4, and I'm going to multiply this whole equation by 3, and I don't have to deal with negative signs at all. So in doing that, this 2 times that 4 would give me an 8w, and this minus 3 times 4 would give me a minus 12z, and this minus 1 has to be multiplied by 4 to give me that minus 4. Let's multiply this whole equation now by 3. So this 3 times 3 is 9w, and 4 times 3 is 12z, and 24 times 3 is 72. And then finally, the z terms will disappear because they are like but opposite in sign, and this 8 and 9 is 17w, and over here I have a 68. And I'm pretty sure 17 divides into 68 4 times. And then finally, I would take that value and plug it back into, I'm just going to go ahead and head into this top equation, one of the original equations. So 2 times w, which is 4, minus 3 times z equals a negative 1. So I've just used the top equation as originally given to me, and I'll have here 8 minus 3z equals a negative 1, and I'll subtract 8 from both sides. Don't forget this negative sign right there. Don't forget that sign right there. negative and a negative adds to be a negative 9, and when I divide both sides by a negative 3, negative 9 divided by a negative 3 is a positive 3. So my answer is W is 4 and Z is 3. And again, I can check that in my original two equations, both of them, to see that they work. And I have done that already, and I do know that they do. So please do that at your leisure. Finally, there's a couple of things that could happen. So when a system has a solution that is an ordered pair for the two variables, things will work out like they have. I'm going to share with you now the situation where when we graphed, wait a minute here. I'm going to look at the two scenarios where when we graphed and the two lines were parallel to one another and there was no solution, or when we graphed and it ended up the two lines lie on top of one another, that there was an infinite number of solutions. I'm going to show you what that looks like algebraically if that were to occur. So here's an example of a system that's in standard form. And you know, sometimes you have to get these in standard form. This one is ready to go, and you might notice that the coefficients in front of the x terms and in front of the y terms are equal and opposite in sign. Wow, that's unusual. So when I add those, I get nothing. When I add those, I get nothing. So I have to put the 0 down, and a 4 and a negative 4 is nothing. When the variable terms disappear and you have a true statement, this is a true statement. This is that situation where the graphs of those two lines are identical. They lie on top of one another. There are an infinite number of solutions. And that's all you need to tell me, is that there's an infinite number. On the computer, they ask for a particular symbol. I can't remember what it is right now in Course Compass. I think they ask for an N for no solutions, and I'm not sure for an infinite number, but do pay attention to those directions. The next example, so again, you got a true statement, you have an infinite number of solutions. The next example I have for you, when looking at this via elimination, ends up being a situation like this, where the variable terms still disappear again, which is, you know, typically you're not used to that. X's are gone, Y's are gone, so put a 0 down. But on the right-hand side, make sure you carefully add these. It happens that they're the same. I didn't mean to do that. But if you get a statement that is not true, there is no solution to this system of equations. It is that situation where the graphs of those two lines don't intersect because they are parallel to one another. This concludes the three methods for solving a system of equations. First, we solved graphically, looking at a graph of the two straight lines to see where they intersect. Secondly, we solved by the substitution method, which meant taking one of the equations and isolating a variable for the rest of the expression, for the rest of the equation, and substituting that into the other equation to solve for one of the variables. And finally, the elimination method. You get to choose. We're going to look at some applications, which method you would like to use.